Hello friends, welcome to this video lecture on System of Particles and Rotational Motion, Part 3 of Chapter number 7 of Physics for Class 11. This particular lecture is about equilibrium of a rigid body. In the previous section, that is Part 1 and Part 2 of the video lecture of chapter number 7, we studied about center of mass, motion of center of mass, linear momentum of a system of particles, vector product of two vectors, angular velocity and its relation with linear velocity, torque and angular momentum. This is a bit lengthy topic and requires your utmost attention. Though the approach is very simple, but it is lengthy. Please note down all the important points. If you feel that I am going very fast, please pause the video and view it repeatedly. Hence, I welcome you once again. Equilibrium of a rigid body. In this section, we will study about the motion of rigid body only, but not the general system of particles. We will also consider only the external forces without mentioning or using the adjective external. Here, forces means external forces only. Please recapitulate. We had derived the equation for linear momentum as dp by dt is equal to 0 or p is equal to constant, as well as we had learned about the angular momentum equation dl by dt equals sigma tau. Hence, we will be using these two relationships and beyond these in this chapter. So let us start this chapter 7.8, that is equilibrium of a rigid body, by defining the equilibrium. A rigid body is said to be in mechanical equilibrium if both linear momentum and angular momentum are not changing with time, or equivalently, the body has neither linear acceleration nor angular acceleration. This means point number 1. The total force, that is the vector sum of forces on the rigid body, is 0, which can be written mathematically as vector F1 plus vector F2 up to vector Fn is equal to sigma of I equals 1 to n of sigma I equals 1 to n of Fi, vector Fi. Let it be equation 1. If the total force on the body is 0, that is sigma Fi equal to 0, then the total linear momentum of the body does not change with time. Therefore, equation 1 gives the condition for translational equilibrium of the body. Point number 2. The total torque, that is the vector sum of torque on the rigid body, is 0. That is tau 1, vector tau 1 plus vector tau 2 plus etc. up to tau n, vector tau n is equal to sigma I equals 1 to n of tau I, that is equal to 0. That is torque on the rigid body is 0. Let it be equation 2. If the total torque on the rigid body is 0, the total angular momentum of the body does not change with time. So, equation 2 is the condition for the angular momentum of that is equilibrium of the rigid body. So, equation 2 gives the condition for the rotational equilibrium of the body. The rotational equilibrium condition is independent of the location of origin about which torques are taken. So, the origin may be anything. It need not be origin only. Further, equation 1 and equation 2 above both are vector equations. As you see, Fi is a vector and tau I also is a vector. These are equivalent to scalar equations each. That is, they can be split into three scalar equations. That is, sigma f of ix is equal to 0 or and sigma I equals 1 to n of Fiy equals 0 and sigma Iz is equal to 0. Here please see Fix, Fiy and Fiz are not vectors. They are the scalars. Let it be equation 3, where Fix, Fiy and Fiz are respectively x, y and z component of forces Fi. Similarly, we can apply it for the torque tau. So, and we can write tau of Ix, sigma tau of Ix equal to 0, sigma tau Iy equal to 0 and sigma tau Iz equal to 0. All that summation from I equals 1 to n. Let it be equation 4. Here tau Ix, tau Iy and tau Iz are respectively the x, y and z components of torque tau I. Conditions for equilibrium of a rigid body. Equations 3 and 4 of the previous slide are repeated here. That is, sigma I equals 1 to n of Fix equal to 0, sigma I equals 1 to n of Fiy equals 0 and sigma I equals 1 to n of Fiz equal to 0. It was given in the previous slide as equation number 3, which is reproduced here. Similarly, sigma I equals 1 to n of tau Ix equal to 0, sigma I equals 1 to n of tau Iy equal to 0 and sigma I equals 1 to n of tau Iz equal to 0 was explained in the previous slide and given as the equation 4. Equations 3 and 4 give 6 independent conditions to be satisfied for mechanical equilibrium of a rigid body. The above equations are the conditions for mechanical equilibrium of a rigid body. In a number of problems, all forces acting on the body are coplanar. That means they act in the same plane, that is xy plane, yz plane or zy plane. Then we need only 3 conditions to be satisfied for the mechanical equilibrium. 2 of these conditions correspond to the translational equilibrium. That is, the sum of the components of forces along any two perpendicular axes in a plane must be 0. The third condition corresponds to the rotational equilibrium. Please note, the third condition is for rotational equilibrium. Therefore, the sum of components of the torques along any axis perpendicular to the plane of force must be 0. Since the consideration of rotational motion does not apply to a particle, we have only one equation, F1 plus F2 plus F3 etc. up to Fn equals sigma I equals 1 to n of Fi. Let it be. This was equation 1. Apply to this to a particle. Thus, for equilibrium of particle over particle, the vector sum of all the forces on it must be 0. This is the equation 1. Since all these forces act on a single particle, they must be concurrent. That means all the forces must be acting on a single point. Translational equilibrium and rotational equilibrium. A body may be in partial equilibrium That is, it may be translational equilibrium and not in rotational equilibrium, or it can be in rotational equilibrium and not in translational equilibrium. Please read the sentence once again to understand the principles of partial equilibrium. Consider the figure: a light mass rod AB as shown in figure A above. At the two ends, that is the end A and B of the two parallel forces, that is F and F, acting at A and B respectively in magnitude and act along the same direction. See, the direction of F is same here in this direction and in this direction are applied perpendicular to the rod. These F are perpendicular to the rod. Let C be the midpoint. Please note it is a midpoint of AB. That is CA is equal to CB equal to length A, small a. The moment of forces at A and B will both be equal in magnitude. That is AF into A or AF. But opposite sense. This acts in a clockwise, one acts in a clockwise direction, the other one in anti-clockwise. That is A is anti-clockwise and B is clockwise. The system will be in rotational equilibrium, but it will not be in translational equilibrium because sigma F is not equal to 0. We will consider another case B as shown in the figure, wherein the direction of F on B is reversed. That is, F is acting vertically and its direction of rotation will be anti-clockwise. So the force at B in figure A is reversed. The force at B in figure A is reversed as shown in figure B. Thus, we have the same rod with two forces of equal magnitude but acting in opposite directions applied perpendicular to the rod. So, F is perpendicular but direction is reversed in opposite direction. One at the end A and the other at the end B. Here, the moments of both the forces are equal. Moments are equal because C is the central point. And are equal, but they are not opposite. They are not opposite. They act in the same sense and cause the anti-clockwise rotation of the rod. The total force on the body is 0. So the body is in translational equilibrium, but it is not in rotational equilibrium. Although the rod is not fixed in any way, it undergoes pure rotation, that is rotation without translation. That means it starts rotating. Torque as a couple. A pair of forces of equal magnitude but acting in opposite directions with different lines of action is known as a couple or torque. A couple produces rotation without translation. Please see the figure. We come across opening the lid of a bottle. So our fingers apply a couple to turn the lid as shown in the figure A. Similarly, in the case of Earth's magnetic field exerts equal and opposite forces on the pole of a compass needle. This is a compass needle shown in figure B. It applies forces in the opposite direction. That is, S acts this way and the N acts the other way. These two forces form a couple. These are the two examples. Now let us solve a question. Show that the moment of a couple does not depend on the point about which you take the moments. Please see the figure here. A and B points are there. The forces acting are minus F and plus F. That is, minus F is acting on at the point A and plus F is acting at the point B. R1 and R2 are the positional vectors. Consider a couple as shown in figure below acting on a rigid body. The forces F and minus F act respectively at point B and A. These points have positions, vector positions R1 and R2 with respect to origin. Now taking the moments of force about the origin, we get the moment of couple is equal to sum of moments of the two forces making the couple. Therefore, R1, the distance R1 into minus F is acting on A, plus R2 is the position vector of B cross F. So simplifying, we get R2 cross F minus R1 cross F, because R and F are both vectors. Therefore, simplifying, we get R2 minus R1 cross F. But R1 plus AB is equal to R2. That is R1, it is in this direction. R1 plus AB equals R2 from the figure. And hence, simplifying, AB will be is equal to R2 minus 1. And this is shown in the figure as R2 minus R1. Therefore, the moment of couple, therefore, is AB cross F. So this is the distance AB cross F, which is independent of the origin, the point about which we took the moments of the force. So we started by taking moments about O and end up with AB cross F, which is independent of the forces. Principle of moments. When algebraic sum of moments of all forces acting on the body about a fixed point is 0, the body will be in equilibrium. That is, algebraic sum of moments of all forces acting on the body about a fixed point is 0, then the body will be in equilibrium. This is known as the principle of moments. Consider an ideal lever comprising of a light rod AB of negligible mass pivoted at a point O as shown in the figure. This point O is called the fulcrum. A seesaw on the children's playground is a typical example of a lever. Here, two forces F1 and F2 parallel to each other and usually perpendicular to the lever as shown act on a lever at a distance D1 and D2 respectively. So F1 is acting downwards, F2 is acting at B downwards, and the point O is located at a distance D1, A is located at a distance D1 and B is located at a distance D2. The lever is a system in mechanical equilibrium. Let R be the reaction of the support at the fulcrum. So R is the reaction which is acting vertically upward. That is opposite to F1 and F2. For translational equilibrium, the sum of forces equal to 0. Therefore, that is F net equal to 0. That is F1 plus F2 which are acting downwards minus R which is acting upwards equal to 0. Therefore, rearranging, R is equal to F1 plus F2. For rotational equilibrium, we take the moments about the fulcrum. That is, the sum of moments must be 0. Therefore, F1 into cross D1 should be equal to F2 cross D2. Here, D1 and D2 are load arm and effort arm respectively. Normally, the anti-clockwise moments are taken to be positive. Note R acts at a fulcrum itself and has zero moment about the fulcrum. In case of the lever force, F1 is usually some weight to be lifted. That is, the F1 is some weight to be lifted. It is called the load. F1 is called the load, and its distance from fulcrum D1 is called the load arm. This is the load arm. D1 is called the load arm. And F2 is called the effort. Here the effort applied to lift the load, and distance D2 of the effort from the fulcrum is effort arm. So D2 is the effort arm. Hence we can write F1 cross D1 equals F2 into D2 as load into load arm is equal to effort into effort arm. This equation expresses the principle of moments for a lever. Incidentally, the ratio load to effort, that is F1 to F2, is called the mechanical advantage. So MA is equal to F1 by F2, that is equal to D2 by D1. If the effort on D2 is larger than the load, that is D2 greater than D1, then mechanical advantage greater than 1 means small effort can be used to lift a large load. Apart from the example of seesaw, there are a number of cases which you can find in our everyday usage. Center of gravity. A point where the weight of body acts and total gravitational torque on the body is zero is known as the center of gravity. That is, center of gravity is a point where the weight of the body acts, and at this point if the total gravitational torque on the body is zero. Such a point is called center of gravity. The center of gravity of the body is so located that the total torque on it due to the forces m1 into g, m2 into g, m3 into g, etc., etc., the total torque is zero. If Ri is the position vector of ith particle of an extended body or the rigid body with respect to its center of gravity, then the torque about center of gravity due to the force of gravity on the particle is given by the relationship vector tau I is equal to vector Ri cross mi into vector g. Here tau I is the torque due to ith particle and Ri is the position vector, mi is the mass of the ith particle, and vector g is the gravitational force. The total gravitational torque about the center of gravity is zero. Therefore, the total gravitational torque tau g, vector tau g suffix g equals sigma tau I, that is the above equation, sigma tau I, that is equal to sigma Ri into mi into g vector. This is the equation, and that should be the total torque. The condition for center of gravity is total gravitational torque on the body should be zero. Therefore, we put it equal to zero. Let it be equation 1. In equation 1, vector g is same for all particles. Since g is non-zero, sigma, so G becomes constant and we can take it out. Therefore, sigma MIRI equals 0. That is the equation 1 becomes sigma MIRI equals 0. Remember that the position vectors Ri are taken with respect to center of gravity, not the origin. It is taken, the position vectors are taken from the center of gravity. We have discussed regarding center of mass in section 7.2. According to that, we had calculated the distances x, y, z coordinates are in a 3 dimension as sigma mixi over capital M, where mi is the mass of the ith particle and xi is the distance and capital M is the total mass of the body. Similarly, we had defined for y and z. Please go back to section 7.2, the link for which is given in the description part of this video. So, center of mass, we had calculated distance x equal to sigma mi over sigma mi xi divided by capital M. If the sum is 0, the origin must be the center of mass of the body. Thus, the center of gravity of the body coincides with the center of mass in uniform gravity or gravity free space. That means if the mass is uniform of the body uniform and or if the body is located in a gravity free space, then center of gravity coincides with the center of the mass. Next point. If vector g, acceleration due to gravity, varies from part to part of the body, then the center of gravity and center of the mass will not coincide. That is, if vector g varies if from within the parts of the different parts of the body, then CG and center of mass will not coincide. Please see the figure here, which shows, this figure shows a way of determining the center of gravity of the irregular body. Please observe here, the shape of this body is highly irregular. If you suspend the body from a point like A, that means this is S is a fixed point. If you suspend this body from point A, the vertical line passing through A coincides with the G as shown in the figure, and mark the vertical. When you suspend this body from point A, you can join, it is suspended vertically, it passes through the center of gravity G and A dash. If you join A dash, mark it vertically. So then suspend this body again from point B and point C, and you get the points B1 and C1 as shown in the figure. If you suspend from point B, then you will get B1. Join B to B1. Similarly, next step, you suspend from C1 and join C to C1. Then the intersection of this, that is AA1, BB1 and CC1 as shown in the figure, will be the center of gravity. Since the body is small enough, the method allows to determine also its center of mass. If the body is small and mass is uniform, then we can also find out the center of mass. Now we will take up worked example. Question number 1. A metal bar 70 centimeters long and 4 kg in mass supported on two knife edges placed 10 centimeter from each end. A 6 kg load is suspended at 30 centimeters from one end. Find the reactions at the knife edges. Assume that the bar to be of uniform cross section and homogeneous. The figure on the right hand side shows the rod AB. The position of the knife edges are K1 and K2. These knife edges are K1 and K2 and the bar is A to B, AB. The center of gravity of the rod at G, that is this is the center of gravity, is at a center of the length AB, that is the whole length is 70 centimeters. G is midpoint, so AG is 35 centimeters and BG is also 35 centimeters. And the suspended load, the given load 6 kg is suspended at point P. Now let us proceed to solve it. Given AB is equal to 70 centimeters, AG is equal to 35 centimeters, AP is equal to 30 centimeters and PG, the distance between PG is 5 centimeters. And distance AK1, that is knife edge K1, AK1 equals BK2, that is equal to 10 centimeters. And K1G equals K2G equals 25 centimeters. Also, given that W weight is equal to, weight is 4 kg. 4 kg, that is the weight of the metal bar, 4 kg, and the suspended load is 6 kg. These are all given in the question, and K1G and K2G are calculated by subtracting the respective distances AK1 and PK2. R1 and R2 are normal reactions of the support at the knife edges. So these are the support or for the supports K1 and K2 and their normal reactions is R1 and normal reaction at K2 is R2. For translational equilibrium, we write the sum of forces equal to 0. The forces acting are R1 plus R2 minus W1 minus W. Please note only 4 forces are acting. That is the force of R1 and R2 are acting upwards. W1 and W are acting downwards. Let it be equation 1. For considering rotational equilibrium, we take moments of the force. A convenient point to take moments about G is about G. So we take moments around G. The moments of R2 and W1 are anticlockwise. You see here, that is here W1 goes in this direction and R2 is also goes in that direction, that is anticlockwise. Because it is anticlockwise and we take the direction as positive, whereas the moment of R1 is clockwise. See R1, the rotation is clockwise, so it is taken as negative. So for rotational equilibrium, we write minus R1 into K1G plus W1 into PG, this is the distance PG, plus R2 into K2G. K2G, K1G, K2G and PG are distances. R1, R2 and W1 are forces. W1 and W are forces. Let it be question 2. It is given that W is equal to 4 into G, that is mg. Mass is 4 grams and G is a gravitational force. So W is equal to 4.00 G newtons and W1 is equal to 6.00 into G newtons, where G is the acceleration due to gravity. Assume that the value of G to be G equals 9.8 meters per second square. Substituting the distances and all that, we get the distances and the values of W1, we get R1 plus R2 minus 4G and minus 6G equals 0. This is from equation 1. Or we can write R1 plus R2, which are unknown, equals 10G. That is, we are moving these two terms 4G and 6G to the right. So it becomes 10G. Let it be equation 3. Therefore, R1 plus R2 multiplying with 9.8, we get 98 newtons. So therefore, R1 plus R2 is equal to 98 newtons. From equation 2, that is the equation for rotational equilibrium, we get minus 0.25. That is K1G is 0.25. This is the centimeters converted into meters. 0.25 meters into R1 minus 0.25 R1 plus W1G. W1 is, that is PG is 0.05 meters into W1. W1 we have to find out. Plus 0.25 into R2 equals 0. Therefore, R1 minus R2 is equal to 1.2G. 1.2G newtons, that is equal to 11.6 newtons. Let it be equation 4. Therefore, from equations 3 and 4, we can solve for R1 and R2. We get the values 54.88 newtons and R2 is equal to 43.12 newtons. Hence the answer, thus the reactions of the supports are about 55 newtons, approximating 55 newtons at K1 and 43 newtons at K2. This is the answer. Next question, question number 2. A 3-meter long ladder weighing 20 kg leans on a frictionless wall. Its feet rest on the floor 1 meter from the wall as shown in the figure. Find the reaction forces of the wall and the floor. The figure is shown here. AB is the ladder and BC is the frictionless wall. The length of ladder is inclined, that is 3 meter, and the distance between the foot of ladder and the wall is 1 meter. This is given in the figure. So using Pythagoras theorem, we can find the length BC. That is, AB square is equal to BC square plus AC square. Substituting the values, we get BC is equal to 2 root 2. Let us solve it. Answer. Given AB is equal to 3 meter long, AC is equal to 1 meter. From Pythagoras theorem, BC is equal to 2 root 2 meters. The forces on the ladder are its weight W acting at the center of the gravity. D is the center of the gravity of the ladder and the weight of the ladder, that is 20 kg, is the W is the weight of the ladder and it is given as 20 kg, which acts vertically downwards. F1 and F2 are two reaction forces. This is at V, the reaction force F1 is due to the wall and it is pointing on the left hand side. And similarly, F2 is the reaction which makes an angle alpha, which is not shown in the figure, with the horizontal of the wall and the floor. F2 is due to the reaction of floor. Force F1 is perpendicular to the wall since wall is frictionless. Whereas the force F2 is resolved into two components. That is a normal reaction. This is the normal reaction N and the force of friction F. So F2 has two components, vector N and F as shown in the figure. Note that F prevents the ladder from sliding away from the wall. That is, the friction prevents the ladder from moving away from the wall and is therefore directed towards the wall. For translational equilibrium, taking the forces in vertical direction, see the forces in vertical direction are normal N, which is pointing upwards, and the W, which is pointing downwards. Therefore, N minus W is equal to 0. Let it be equation 1. Taking the forces in horizontal direction. So, F which is due to the friction is pointing right hand side, that is from A to C, and F1 is from B towards the left hand side. Therefore, F minus F1 is equal to 0. Now we will take the for rotational equilibrium, the moments of forces about A must be 0. Therefore, F1 into 2 root 2, this is the vertical distance, minus half of W, that is half of the ladder's weight acts downwards, equals 0. Or F1 is equal to W by 4 root 2, that is rearranging equation number 3. Now W is given as 20 kg, 20 kg into G, where G is the gravitational force. Take the value of G as 9.8 meters per second square. Therefore, W is equal to 20 kg into 9.8 newtons. This N is newtons. It is not normal. It is newtons. Therefore, simplifying, we get 196 newtons. From equation 1, that is N minus W equal to 0, N equals W. Therefore, N is equal to 196 newtons. From equation 3, this is the equation 3, F1 is equal to W divided by 4 square root 2. That is F1 is equal to W by 4 square root 2. So W, the value of W we have found as 196 divided by 4 square root 2. Simplifying, we get the value of F1 as 34.6 newtons. This N is for newtons. From equation 2, F is equal to F1. That is equal to 34.6 newtons. So we have found the value of F. Now F2 is equal to square root of F square plus N square, because friction force F and normal reaction to the normal N are the components of F2. Therefore, F2 is equal to square root of F square plus N square. Substituting the values, we get F2 as 199.0 newtons. The force F2 makes an angle alpha with the horizontal, as stated above. Therefore, tan alpha is equal to N by F. that is normal by that force, that is equal to 4 root 2. Therefore, alpha is equal to tan inverse of 4 root 2. And we get from tables the value of alpha as 80 degrees approximately. That is the answer. With this, we have concluded section 7.8 of chapter number 7. This was a very elaborate chapter, hence only one section was discussed. In the next video lesson, we will discuss about moment of inertia, perpendicular and parallel axis, and if possible, we will also take up kinematics of rotational motion. Till then, goodbye.